Okay, so today's notes, we're covering section 6.2. We're building on what we did with random variables earlier. So last set of notes, we talked about what is a random variable, how to calculate the mean, the standard deviation. Those were the two big things. What we're doing today is taking a random variable. We're either multiplying by a constant, adding a constant, we're calculating a new mean and standard deviation. Now, what I will tell you is these two sections tend to come up on multiple choice a lot. And just, this is my warning to you, students tend to forget these. So these are concepts that maybe at the time are not super complicated, but then they pop up in random multiple choice questions and students tend to forget that these exist. So don't let yourself be fooled into thinking that this is super easy. Good news, no new calculator stuff, but this is not on the formula sheet. So let's get started. This is the page that you're looking for, so if you could find this page. And we're going to be coming back to this data set a lot. We're looking at El Dorado Community College. This community college considers a student to be full-time if they are taking between 12 and 18 units. The number of units that a randomly selected full-time student is taking in the following semester has that distribution. Okay, so first of all, how do we know that this is a valid probability distribution? Okay, all of the probabilities should sum to 1. Is this a discrete or a continuous distribution? Discrete, right? Number of units being taken, you can't take 12.35. Drawing a probability histogram. Are you guys okay with that? I don't really want to draw a histogram. We're fine with that. If I ask you to discuss the histogram, what would you talk about? CSSU, right? Center, shape, spread, if there's anything unusual. Okay, I do want us to calculate the mean and standard deviation, though. So do that now. Take 30 seconds. Put these numbers in your list. Calculate the mean and standard deviation, please. Okay, I got a mean of 14.65 and a standard deviation of 2.056. Do we agree? Okay, great. Units follow whatever the units of the data set is. This is number of units that a student is taking. None of that is new, that is just review. We okay with that? Okay. So then here's where we're getting into some new stuff. At El Dorado Community College, the tuition for a full-time student is $50 per unit. If T is the tuition charge for a randomly selected student, we can write T then is 50 times X. So what that means is if you are taking 13 hours or 13 units and you get charged $50 a unit, 13 times that 50, you're being charged $650. So this now is the probability distribution for T. And again, all these numbers represent is $50 per unit. So if you're taking 18 units, 18 times $50, you're being charged $900. That makes sense? Okay, what I want you to do now, calculate the mean and standard deviation of T. Okay, so let's talk. I didn't do this, so hopefully you can give me some numbers. What did we get the mean of T to be? 732.5. Is that what I heard? Okay, standard deviation of T? Casey? 102.8, about? You guys agree? Okay, so what I'm trying to see here, if we take a bunch of numbers and multiply them by 50, does it change the mean? Did our mean change? Yeah. Did our standard deviation change? Okay, and what I want us to notice is our mean got 50 times bigger, our standard deviation got 50 times bigger. Right, so if we had taken this number and multiplied by 50, we would have gotten 102. If we took 14.65, multiplied it by 50, we would have gotten 732.5. So that leads us to this first piece. What is the effect of multiplying or dividing a random variable by a constant? So we took that random variable x, we multiplied by 50. What did it do? What do you think it did to the shape? Do you think it changed the shape? Okay, shape, no change. If it were a normal distribution before, it's still a normal distribution before. Now, if it were symmetric, still symmetric. The center, so in this case, the mean, is going to multiply or divide by that same constant. So if instead we had decided to divide by 2, we would just need to divide the mean and the standard deviation by 2. And then the spread is changed by the same constant. Okay, so now we're going to look at an example where we are adding a constant. So in addition to tuition charges, each full-time student is assessed student fees of $100 per semester. So let C be the overall cost for a randomly selected student. So here is our formula now. C is equal to 100 add T. So what we're doing is we're taking the tuition above, and then the student has to pay an extra $100. We're going to calculate the mean and the standard deviation again. I'm just going to tell you what they end up being. If you had to guess them, if you took a whole bunch of numbers and you added 100 to every single one, do you think it's going to affect the mean? Right? The average is going to get bigger. Is it going to affect the standard deviation? No, picture a dot plot, right? If I add every 100 to a dot plot to every number, doesn't it just move the distribution? It doesn't change it. So we don't even have to do a calculation down here. We already know the mean of C is going to be 100 bigger. So it's going to be 832.5. Standard deviation of C, though, is going to remain the same. Still going to be 102.8. Okay, so that leads us to, what is the effect of adding or subtracting a constant? Change to the shape? No, no change. Spread? No change. The center is the only one that's changed. And it is changed by the same factor. Linear transformation, we're not going to write down. It's just doing both the multiplying and the adding. So what we're going to do is we're going to do one more example together. We'll take a break, and then we will do a few more examples. This is the gist of today's notes. So let's do, like I said, one more example together, and then we will take a break. In a large intro stats class, the distribution of X, which is equal to the raw scores on a test, was approximately normally distributed with a mean of 17.2 and a standard deviation of 3.8. The professor decides to scale the scores by multiplying the raw scores by 4 and adding 10. A, define the random variable of Y to be the scaled score of a randomly selected student from this class. Find the mean and standard deviation of Y. Before we do A, let's write down what we know. So first thing, we know what X is, and we know that X is normally distributed. We know the mean of X is 17.2, and the standard deviation of X is 3.8. here is what is absolutely most important. In part A, before we can find the mean and standard deviation of y, we need to know the relationship between x and y. So on the previous page, we got equations such as this, t equals 50x, and then we got c is equal to 100 add t. These are called rules or formulas. You have to do that. Don't just start jumping in with numbers and multiplying and adding. You need a rule. So if I got, let's say, a 30 as the raw score on the test, how do I figure out my new score? If I got a 30 on the test, how do I figure out my new score? Based on what the professor's doing. Multiply by 4, and then add 10. Okay, so the new score then is going to take the old score, multiply it not by 30, multiply it by 4, and then add 10. Or it could be written as 4x add 10. Okay, if I want to find the mean of y then, if I multiply all these scores by 4, does it affect the mean? The mean's the average. If I add 10 to everybody's score, does that affect the average? Yes, for sure. So the mean of y, we're going to take 4 times the mean of x and add 10. And so we get the mean of y to be 78.8. Standard deviation of y. If I multiply all the scores by 4, does it change the spread? If I add 10 to all of the scores, does it change the spread? Okay, this is the one that I think we always have trouble with. Think of two numbers. So this is just my example. If I think of the numbers 1 and 2, the difference between them, the range, is just 1. If I multiply those numbers by 4, so I get to 4 and 8, does it change the range? Yeah, right? I now have a range of 4. If I take those numbers and I add 10, so I have 11 and 12, does it change the range? No, it stays the same. So if we think of it that way, we can tell 4 is the only number that changes the standard deviation. Adding 10, all it does is shift the distribution. It doesn't change the spread, though. So this is going to be 4 times that standard deviation. So we get a standard deviation of 15.2. Okay, so then in B, what is the probability that a randomly selected student has a scaled test score of greater than 90? So we're looking for the probability that y is greater than 90. What do we know about y? Well, we know the mean, the standard deviation. What else? If x is normally distributed, y is normally distributed, right? Adding, multiplying is not going to change the shape. So we're going to say that y is normal. The mean is 78.8. The standard deviation is 15.2. Remember in the book sometimes changes these to z-scores. You don't have to do that. Please don't. It's a waste of your time. So we have mean, 1 standard deviation, and 2. So the mean is 78.8. If I add 15.2, I think I get 94. So this is just showing my work. So I'm looking for a scaled score of 90 and higher than that. And at this point, how do I calculate that area? Come on, guys, speak up. What do I do on the calculator? Normal CDF? Normal CDF? Okay, beautiful, do that. Normal CDF. My lower bound is 90. My upper bound is some really big number. The mean is 78.8, and the standard deviation is 15.2. So I get a probability of 0.231. Can anybody confirm that? How do I know that that is in fact reasonable and not totally abnormal?
The 68, 95, 99.7 rule, like it's within like 20-ish, so it's less than the, like if 16 is the
Okay, I'm with you. My mind does not go there, but thank you. So Alex is saying by the 68, 95, 99.7 rule, 16% is more than one standard deviation away, so we have to be bigger than that. I was just looking for the area. Looks like it might be 0.231. So you went a lot further than me, which is great. Okay, how do we feel about this? Okay, so we've got 3 more examples that we're going to do together. So let's keep going. Suppose that the height m of male speed daters follows a normal distribution with a mean of 68.5 and a standard deviation of 4, and the height f of female speed daters follows a normal distribution with a mean of 64 and a standard deviation of 3. What is the probability that a randomly selected male speed dater is taller than the randomly selected female dater he is paired with? Okay. I don't really care about the context. What we're doing with the numbers is most important. What do you think we should probably start with? What best practices for stats students? Writing down what we know. Okay, so we have m is the height of male speed daters, and we know that m is normally distributed. We know the mean of m is 68.5, and we know the standard deviation of m is 4. We also have f, which is the height of female speed daters, and we know that f has a normal distribution, that the mean of f is 64, and standard deviation of f is 3. So that's step 1. Whatever you've been told, put it in probability notation. Step 2, write what you are asked for. What is the probability a randomly selected male is taller than the randomly selected female? So m is the height of the male, f is the height of the female. So we are looking for the probability that the height of a randomly selected male is taller than a female. Okay, this we have not done before. We cannot just simply put numbers in here. So what some people want to do is they say, well, the females have a height of 64, so I'm just going to put 64 in there. That's not the same. That would be saying that the male is taller than 64 inches. That's not what we're looking for. We have no idea the height of the man, no idea the height of the woman. We just want to know, is the man taller than the woman, regardless of how tall, whether he's the average or above the average or whatnot. So what we're going to do is we're going to move female to the other side so that the two variables are on the same side. So we are looking for the probability that m subtract f is greater than 0. This m subtract f now is almost like a new variable. So if we look here, if we look at m subtract f, if m is normal, if f is normal, when we subtract them, we're still going to have a normal distribution. The mean is exactly what you think it would be. We're just going to subtract. So 68.5 subtract 64 would give us a mean of 4.5. The standard deviation is not what you would think it would be, though. So most people would just go, oh, I'm going to take 4, subtract 3. That's not the case, though. So the standard deviation is the hardest one to remember. Here's what you need to know. first of all, we can only calculate standard deviation if these variables are independent. Now, we are assuming that we have a group of male daters, a group of female daters, and we're just choosing one at random. But it's very important, so if you could write this down, M and F need to be independent. Anytime you are taking two variables and putting them together, spread has to get bigger. If I'm taking two data sets, putting them together, my variability must get bigger. So that means I always have to add. So even though we're subtracting M and F, when we find spread, we have to add. The other thing to remember is you are always adding variances. So this is a key. Always add and always variances. So this is going to give us 4 squared add 3 squared. So our new variance is 25. When we take a square root, then, we get a standard deviation of 5. So regardless of what's happening here, you always have to add, and it always has to be variances. Think of it kind of like Pythagorean theorem. Always square, always add. Now, this is just a plain normal distribution problem. So now we can draw our curve. We have mean, standard deviation. I'm using these numbers right here. So the mean is 4.5. Standard deviation is 5. And we're looking for the probability of being greater than 0. So 0, let's say, is about here. So we're looking for all of this. And like we just did before, plain old normal CDF problem. So we get a likelihood of about 0.816. Just as a review, if I asked you to interpret this, you would say something like, in the long run, we chose many speed dating pairings in about 0.816 or 81.6% of them, the man would be taller than the woman. Okay. Questions before we look at one more? No? So let's look at this one at the top. I would say this example that we're going to do is probably the one that students get wrong most often. So hopefully we don't. Suppose that a certain variety of apples have weights that are approximately normally distributed with a mean of 9 and a standard deviation of 1.5. If bags of apples are filled by randomly selecting 12 apples, what is the probability that the sum of the 12 apples is less than 100 ounces? Okay, I'm going to start by writing down what I know. I don't have a variable, so I'm going to define A to be the weight of an apple. And we know that A has a normal distribution. We know the mean of A is 9. And the standard deviation of A is 1.5. We are looking for the probability that the sum of the 12 apples, sum of 12, is less than 100. So I'm going to say S is the sum of the 12 apples. And we are looking for the probability that that sum is less than 100. So this is everything that we've been given and that we are looking for. Please do not just start jumping in with numbers. Like I said in the last one, we need a formula or a rule for the relationship between A and S. Here's what most people do wrong. They say the sum of the apples is 12A. If we think of what this is communicating is I weigh one apple, multiply it by 12, and that will give me the sum. Real life, is that the case? No. This would only be the case if all the apples had the exact same weight, do they? No. So this does not work. Instead, we would have to weigh the first apple, the second apple, all the way up to the 12th apple to know the sum. We can't just take one apple and multiply by 12. So then, if we want the mean of S, we have 9 for the first apple, 9 for the second apple, all the way to 9 for the 12th apple. So the mean of S then would be 108 ounces. Standard deviation of S is the more difficult one. Like the last example, if we are combining variables, we always have to add. So we're going to be adding. And it always has to be variance. So we have standard deviation, which is 1.5. So to get variance, we would need to square that. So there would be 12 of them. And then we would have to take the square root to get standard deviation. So there are 12 of that 1.5 squareds, and then we would take the square root, which gives us 5.2. Okay, so before we can calculate that probability, we need to put it together. S is going to be normal. If the apple weights are normal, if we add a bunch of them, the sum is also going to be normal. And then we now know that the sum has a mean of 108 ounces and a standard deviation of 5.2 ounces. Now it's just a regular normal probability question. So our mean is 108. So this would be 102.8, 100, I don't know, somewhere there. And again, we would just do normal CDF. If you trust me, I will tell you the answer ends up being 0.0620. How do we feel about this? Okay.